learn. But effectively, this is a topic area that could have actually taken a whole course quite easily at third year level. And there are so many different aspects of ore geology when you get down into the details of it that, you know, with 6 lectures and 3 labs, it's almost impossible to cover everything. So what we're trying to do in this set of lectures and labs is just to give you the first sort of overview of where different types of ore deposits can be found, what kinds of things we do to go about identifying them, some of the process, some of the Earth's surface processes and the subsurface processes that go on in terms of creating and enriching these deposits, and then some of the environmental impacts in a short and general sense. So in the lab, again, since we've only got such a small amount of time, we're not going to take you through a microscopy course in ore geology. That would be a very long, complicated process, but we are going to give you an opportunity to have a look at some of these rocks and hand specimens and start trying to understand the different ores that we're going to, mostly people will come across and work. So I'll pass you on to Marco Brenner. So Marco is a PhD in volcanic geology, but has spent a bit of his life in Australia as well, and his undergraduate degree was actually in a mining school, and so he's done a little bit of work in and around mines in Australia. And so Marco will take you through the first one of these lectures. So any questions, you can direct them to either myself or Marco. Our addresses are there, and we'll be loading up the lectures on what's called a Cecil after the lectures happen. So we're moving to a new system called Canvas. So we're getting used to Canvas, Talus, Cecil, all these names going in and out. So next year, everything will be on Canvas, because we've just been through this big course about Canvas training.
Do you know how to get rid of? Do you like having both screens on? Yes. There's no whiteboard.
Okay.
Finally. Very well. Thanks for the introduction, Shane. Goodbye. Well, if you found this lecture, it means you know where you have to be. And a reminder that the labs are going to be tomorrow. The first one from 9 to 11, and the second one from 4 to 6 in room 406 of the Health Science building, which is just next door. And you should try to make it at least to one of them. And if you want to come to both, feel free. These are the 2 textbooks that I will be basing this course on. They are more or less equivalent. If you look through them, the ore forming process is available in the library and on fourth loan as well. Both of them should be available in the bookshop, copies of them. As I said, they are basically equivalent. The ore forming processes, one is maybe a bit more theoretical, with and the ore deposit geology book. It uses more deposit-specific example to explain processes, and might be a bit more relevant to Australia and New Zealand. Other resources that you can easily find, the Elements magazine, which I will also be using every now and again, is available through the library website. If you go on the search engine and type Elements magazine, you should end up with a link to the website where you can download PDFs of that. And that's another textbook, Geology of Ore Deposits, or GOD in brief, which you can find in the library. So, I guess Shane's already mentioned this, but just to remind you of what you should get out of this module. Basically understanding the processes that lead to ore deposit formation, and know the relationship with certain metals and certain deposits and where they occur, and gain a bit of familiarity with major ore minerals and some ore deposits that will be done in the labs. And a few modifications to the outline of the course that you received, I guess, at the beginning of the semester. So we will have 6 lectures dealing, well, today bit of an introductory lecture, and on Wednesday we'll be looking at magmatic ore deposits, and next week hydrothermal related ore deposits, and the last week one lecture on sedimentary and supergene processes, and the last lecture a bit of a revision. The labs tomorrow we'll be looking at oxide ore minerals. It's going to be a very slightly light lab. Next week sulfides and some related ore deposits. And the last week we will be looking at BHMS related associations. And if you don't know what BHMS, don't worry. For now we will look at them in due course. And there'll be a small exercise with assessment worth 2.5% of the course. The remaining 10% of assessment, of coursework assessment, will be on an assignment, and this will be here, and it's going to be detailed in a PDF that I will upload on CESL. So, as you can see, you've been invited, and you cannot refuse, to write a short review article for the New Zealand Journal of Geology and Geophysics on one of the following topics: either diamond, opals, or seafloor manganese. And you can choose whichever. None of these topics is going to be covered in the lectures, so none will be particular advantage. And you should discuss not only the history, the use, the occurrence, the genesis, and all the other aspects of these deposits in about 2,000 to 2,500 words, with figures where they are appropriate. And you should use the style and editing style and referencing style of the New Zealand Journal of Geology and Geophysics, which you can find. This address comes out with a PDF or instruction for authors. And this is going to be due at 9 AM on Friday the 23rd, which is the last day of the semester. In the assignment box outside Shane's office, and it's, as I said, 10% of the course assessment. So I think we've gone over this, or Shane went over this. Today we'll be looking at a bit of history of metals and society, then what ore minerals and ore deposits are, how they are exploited through mining, and the environmental impacts. So, as you probably know, metals are quite important to society, and hopefully that's why you chose this course. From basic gadgets that everyone should have, as you can see, every single component of a mobile phone contains some kind of metal rather, to also everything else, infrastructure, buildings, airplanes, the camera that I used to take the picture, the economy, and just switching the lights on and off. All relies on metals, and therefore it's important for us to understand how ore deposits forms and how metal deposits they can be exploited. And this is a brief history of metals, and you can look at them in more details in your spare time. But just humans have always been fascinated, particularly by gold. They started using it 8,000 years ago, and then later they started extracting copper and making weapons, and hence we had the Bronze Age, when people started going from throwing rocks at each other to throwing metal sticks at each other, and then later on they found out how to extract iron from ore minerals, and they started throwing iron stick at each other. And so we have the Iron Age, and later on more metals and uses were found, with the last metals still discovered in the 1900s. And as I said, you can go through those in your own time. So probably the reason why gold and copper were exploited first by mankind is because they occur as native metals. So like here gold, copper, silver. These can be found in nature as is. So they are most easily extracted and employed for whatever use mankind wanted to make of them. However, well, most metals don't occur as native, and they occur as ore minerals or within ore minerals. And there is a plethora of them, and you can see the periodic table at the bottom here. And certain elements like to occur as oxides, and others are sulfides like nickel and copper, and some metals like iron like to occur both as oxides and sulfides. And these are a few examples that we are also going to be looking at during the labs. Hematite, chromites, cassiterite are examples of sulfides, of oxides, sorry. Chalcopyrite, pentlandite, and molybdenite. Some of these are tunnel twisters. Examples of sulfides and carbonates and sulfates also can be used to extract useful metals. Now, what's the definition of ore? So, based on this textbook, any naturally occurring material from which a mineral or aggregate or value can be extracted at a profit. So, and there are a variety of definitions of what ore is, but usually they all agree on 2 points: that a metal can be extracted and it needs to be extracted at a profit. Otherwise, there's no point doing it. And other words related to the ore forming process are ore bodies, ore shoots, ore deposits, ore reserves. And ore deposit types have also been kind of grouped into different categories, depending on, for instance, what commodity is extracted from them, whether it's copper, iron, or gold, the type of hosting rock, whether it's metamorphic rock, sedimentary rock, the tectonic settings, whether the deposits occur in arcs or back arcs or intraplate settings. What we will be focusing on during this series of lectures will be the genetic processes. So, as you all know, rocks, the 3 rock types, main rock types, we have igneous, metamorphic, and sedimentary. Likewise, ore deposits can be grouped as igneous, hydrothermal, and sedimentary or superficial. And these will be treated in lecture 2, 3, and 4, and 1. This is just an example of an igneous ore deposit. This image should be rotated 90 degrees so that the bands are horizontal, because this was formed in a magma chamber where we have magma injected into the crust, it's crystallized, and this layer of anorthosite, which is a cumulate of feldspars, then here a band of chromitite, which is a cumulate of chromite, and above it pyroxenite, which is a cumulate of pyroxene. So you can imagine a magma chamber where different minerals were settling at different times. Then we can have hydrothermal deposits, and they often occur in veins. Like this is the surface of a vein with cinnabar, or they can occur with hydrothermal solution infiltrating in porous medium, such as this was a conglomerate, quartz pebbles, and a solution percolating through the porosity and forming pyrite and pyrrhotite. And sedimentary deposits precipitated from water or solution near the surface. This is a beef Vanderdyne formation, not to be confused with beef, the one you eat. It happened. Some people. But these are bands of chert and shales and some oxidized layers, which can then become enriched and form this massive hematite or bands. But of course, nothing ever happens black and white, so processes overlap, and we can go from kind of late stage magmatic processes that overlap with hydrothermal ones, or enrichment of primary methodion formation through migration of fluids, and other supergene and secondary processes that can make primary ore deposits actually viable. So, as you can gather, fluids can be quite important for ore forming processes because they can carry, well, first of all, they carry metals in solution, and they can promote fluid rock reactions, which precipitate metals. And these are the variety of types of fluids that are associated or you can find in the earth. They've got magmatic fluids, can be silicate or oxide, carbonate, sulfide, dominated. And often, or towards the end of the crystallization process, then we get water-dominated fluid. Metamorphic fluids that are derived from high pressure, high temperature modification of rocks. So the rock, when it's undergoing metamorphism, it starts to sweat and release fluids that are rich in metals, which can then go migrate and precipitate the metal cargo somewhere. And also we have other types of waters, such as meteoric water, seawater, and connate water, which is the water left within pore spaces during sedimentation. And an example of that would be the liquefaction that occurred in Christchurch during the earthquakes in 2010. And 11. Basically, we had water and sediments, so the water presence in the pore space of the sediments, and the seismic waves shaped the sediments and basically created a compaction of the sediments, and the water escaped. And the way to escape was towards the surface and formed liquefaction. And mud volcanoes. So as you know, not every rock makes an ore deposit, although every rock arguably contains a little bit of gold and iron and whatever other element you want. So we need a process that enriches the metal before we can extract it, the product. This is an example from northern South Island, Blue Mountain, which is a layered intrusion, basically a small, relatively small layered intrusion with gabbros and pyroxenides. Some exposed here in the foreground and further up towards the top of the mountain. And layered intrusions are often related to ore deposits, as you can remember that picture of the igneous deposits showed with the anorthosite and the chromite and the pyroxenite. However, early geologists went and looked at this place, and they could find no significant metal enrichment that would warrant further work on it. Why? Well, different metals need different degrees of enrichment in order to become viable. So for instance, depending on the concentration in the crust and the grade in a typical ore. So for instance, up at the top we've got aluminium and iron, which are quite abundant in the crust, and the ore minerals contain actually quite a lot of iron. So they need to be enriched by relatively small factors. Whereas at the other end, gold and platinum are very rare in the crust. The typical grade in the ore is quite low, and therefore they need to be enriched by several orders of magnitude. And that controls whether we have a mineral resource or a mineral reserve. So mineral resources have been identified through exploration and prospection. And the geologists have found that, okay, there is something of interest in place. But in order to make it a mineral reserve, that needs to be economically viable. And to wake up, tell me what factors control whether a deposit is economically viable or not. Any ideas? If you were a mining company executive and you had to decide whether to invest in a project or not.
How much of it is there?
Pardon?
The quantity of
Yeah,
the...
yep, that's one. Quantity, volume, accessibility. What else?
Is it expensive or not? Whether it's valuable or not?
Uh,
Actual work?
You mean the price?
Yeah.
Yeah, yeah.
Your investment? Like, if it's going to be profitable?
Well, that's kind of a result of the decision process. So the properties of the reserve or the resource do not control it. That's an outcome.
Yeah.
Any more? We identified some, but these properties can be inherent to the deposits, such as, we said, the volume, geometry of the deposit, whether it occurs focused or dispersed, so maybe massive sulfides as opposed to disseminated sulfides. The overburden, which is the material on top of the deposit that you have to get rid before starting mining. So the ease of access, if something is just on the beach or on top of a mountain, there'll be different problems of getting to the ore. The mineralogy, so what is the deposit made of, whether there are any impurities or whether there are any byproducts that could be also exploited to make a profit. All these can be external, as we've seen, the price of the metal on the financial market, legal and political issues. If you want to mine in New Zealand or mine in the Republic of the Congo, there might be different issues you have to consider. You might not need armed guards in one of the places. And environmental considerations, which in some countries are imposed by governments and in other countries less so, nevertheless. So, what's the process of finding ore deposits? And we start with exploration, where we start with a kind of large-scale area, and we get airplanes fly above it. We get geophysical surveys, such as magnetic surveys or gravity surveys, and then the geophysicists back at the office look at these maps and say, oh, there is an anomaly here that corresponds to an anomaly there. So that might be interesting to further explore, and so the chief exploration geologist decides to send a couple of geos off to the ground and investigate further. So you get to the field and start taking samples, such as was the case here. This is again a map of Blue Mountain. Geologists